Hello and welcome to the next video in this short series of videos about noise in electronic circuits. This time, quantization noise. Well, quantization noise is the noise that's introduced by the process of analog to digital conversion. Here we've got an example of an analog to digital converter with a 3-bit output. That means its output can be in any one of these 8 states only, from 000 to 111. The input analog signal, this blue signal here, however, can take any possible value within the range of the ADC's input. That means that in the process of going from the analog value to the digital representation of it, there is a little error voltage introduced. Here, the analog signal is slightly smaller than the digitized signal, so the error is positive. I'm defining the error here as being the difference between the digitized version, this value here, and the actual analog input signal itself, this value there. And this error signal here behaves like an additional noise. It has an RMS value, it has a probability distribution, and it has a noise power. And you can treat it just like noise, a noise signal adding on to the analog signal, which produces this digital signal, stepped digital signal, which is the actual output of the analog to digital converter. Unlike the thermal and shot noise that we've seen before, however, this noise is not Gaussian. This noise has a restricted range of values. It is always in the range of +0.5 to -0.5 of the gap between two adjacent voltage levels. If we consider an ADC with n bits, then there are 2 to the power of n possible different output states that ADC can be in. If the input range of the ADC is from -a to +a, then there are 2 to the power of n possible states in between that range. The maximum possible error is half of the gap between 2 adjacent stages. And if there are 2 to the n stages in a range from +a to -a, then the gap between 2 of the stages must be 2a divided by 2 to the power of n, which means that the maximum possible noise voltage is half of that, and the minimum possible noise voltage is -half of that. The noise voltage must be somewhere in that range always. We usually assume that the probability distribution is uniform within that range. And that's a good assumption provided the amplitude of the wave that you're digitizing is much greater than the difference between 2 adjacent levels, which in practice it always is, otherwise you get really terrible quality signals out of your analog to digital converter. So if we know the range, we can work out an expression for the probability distribution of this form of noise. Here we know that the amplitude of the noise must lie in the range from a over 2 to the power of n to -a over 2 to the power of n. I've just cancelled those 2 in the expression there to get these limits. And with a uniform probability distribution, that means the probability distribution curve would look like this. The amplitude there, the height of the probability distribution, is determined by the fact that the integral of the probability distribution over all possible values of x from -infinity to infinity must be 1, because the value of x has got to be somewhere in that range. So if we add up the probabilities of any value in that range, the answer must come to 1, which means that the area of this rectangle, which is the integral of px dx, the area of this rectangle must be equal to 1. Well, if the area of this rectangle is equal to 1 and its width is 2 times a over 2 to the power of n, then its height must be 2 to the power of n divided by 2a. So this area of this rectangle is equal to 1 as required. So that gives us the probability distribution of our uniform quantization noise. 2 to the power of n divided by 2a. Knowing the probability distribution allows us to determine the mean noise power. All we have to do that calculation is to say, right, well, we know that the probability distribution looks like this. Let's add up the contributions towards the average noise power from every single little possible value of x, the noise voltage. Well, let's take the range from x to x plus delta x there. The contribution to the mean power from that range of values is x squared. That is the square of the value of x, so that's the power associated with this value of x, and it happens px delta x of the time. If I continue and add in the values of all of the other possible values of x, and then add up all of those noise powers, I would get the total noise power. And that's just the integral from minus a over 2 to the power of n to plus a over 2 to the power of n of x squared px dx. I'm adding up the powers rather than adding up the voltages because they're independent noise sources. I have to add their powers if I want the total noise power. Okay, that is a fairly straightforward integral to do. That just gives us x cubed over 3 times p of x, which is a constant, and equal to 2 to the power of n over 2a, evaluated between a over 2 to the power of n and minus a over 2 to the power of n. Substitute in for these values of x and we end up with 2 to the power of n over 2a times 3 times a cubed over 2 to the power of 3n minus a cubed over 2 to the power 3n, which is 2 to the power of n over 2a times 3 times 2a to the power of 3 over 2 to the power of 3n. Right, 2 to the power of n divided by 2 to the power of 3n is just 1 over 2 to the power of 2n. That 2 cancels with that 2. A cubed over a is just a squared. And that 3 at the bottom has to stay at a 3 at the bottom. And we end up with that as our total average noise power. A squared over 2 to the power of 2n times 3. If I wanted to express that in terms of a RMS noise voltage, I'd have to take the square root of that and say the RMS voltage is just A over 2 to the power of n times the square root of 3. Just the square root of this. It's usually more interesting if we determine the signal-to-noise ratio rather than just the amount of power in the noise. And in an ADC, we can do that fairly readily and get a fairly interesting result because we know what the maximum signal can be. If we've got an ADC digitizing everything from plus A to minus A, then the maximum amplitude of a sine wave that can be digitized by this ADC is a 0 to peak amplitude of A. A sine wave with a 0 to peak amplitude of A has a power of A squared over 2. So I can determine the signal-to-noise ratio, the SNR, which is always expressed in terms of power, the signal power divided by the noise power. That's the signal power, A squared over 2, divided by the noise power, A squared over 2 to the power of 2n times 3, and that gives this expression here. Signal-to-noise ratio is 2 to the power of 2n times 3 over 2. Or if you wanted to write it as 2 to the power of 2n minus 1 times 3, that would be fine as well. It might be helpful to put some numbers into this calculation. I've written maximum here because this is the maximum signal-to-noise ratio you can get. Maximum because this is with the maximum signal power, the largest amplitude sine wave that will fit within the range of the analog to digital converter. Okay, let's suppose we have an 8-bit converter. With an 8-bit ADC, plug the numbers in, and the maximum signal-to-noise ratio ends up being about 98,000, which expressed in dB terms is about 50 dBs. If I move up to a 16-bit converter, then the signal-to-noise ratio with a maximum amplitude sine wave coming in ends up being 6.4 billion, which in dB terms is about 98 dBs. For a while that was the standard in the audio industry, but now we can get much higher resolution ADCs than that. A 20-bit ADC will give you a theoretical maximum signal-to-noise ratio of 1.6 trillion, which is 122 dBs. And you can now get 24-bit ADCs. And they give you a maximum signal-to-noise ratio of about 422 trillion, which in dB terms works out to be 146 dBs. To illustrate just how big a range that is, a 50 dB signal-to-noise ratio, that would be about the signal corresponding to a typical conversation in an inside room. The kind of level that I'm talking to now as the signal, and the noise would be at the very limit of your hearing range. Move up to a 16-bit ADC, keep the noise at the very limit of what you can detect with the ear, and the maximum amplitude would be about that of a lawnmower or a motorcycle. Go up to a 20-bit ADC, the range there, from the minimum possible amplitude detectable by the human ear, up to a loud thunderclap or a chainsaw. The type of thing that normally you would be advised to use earmuffs with. 146 dBs, and that's the difference between the minimum level of noise that your ear can detect and the amount of sound that would rupture your eardrum. And yet, these ADCs are perfectly available. For example, this one up here is a 24-bit stereo audio codec. Now, for the sake of accuracy, I should point out that I haven't considered here any non-linear effects of the analog to digital converter. I've assumed that it is accurate enough to have all of its 2 to the power of 24 different levels equally spaced in voltage. And no ADC can do that. So there is an additional distortion caused by the fact that it's not an ideal analog to digital converter. And it's the sort of performance that people use in professional audio these days. The ear is incredibly sensitive. Okay, that's all I wanted to say this time. Next time, moving on to looking at some alternative ways to characterize the noise performance of amplifiers and components.